Picture a city with no engines, no fuel, no electricity, no steel. A city that moved mountains using nothing but physics and human will. A city that existed 2,000 years ago and delivered more water per person than New York does today, by a long shot. New York, the most infrastructure-advanced city on the planet, 120 gallons per person per day. Ancient Rome, in the 2nd century AD, 290 gallons per person per day, 2,000 years apart, and Rome was winning. 11 aqueducts, 290 million gallons of water delivered every single day. Enough to fill an Olympic swimming pool every 4 minutes. No pumps, no electricity, just physics. Most of these structures are still standing, not as museums, as functional engineering. They survived wars, earthquakes, and 2 millennia of weather, while modern bridges collapse at 50. How did they do it? That's the question modern engineering still can't answer without a degree of embarrassment. And that's exactly what we're about to find out. To understand what the Romans built, you first need to understand the scale of the problem. Rome in the 2nd century AD had 1 million inhabitants, a real metropolis, with no navigable river inside the city, no accessible groundwater, not enough rainfall in summer. Water had to come from outside, from the mountains, from rivers miles away, in some cases from sources over 55 miles from the city. It had to arrive with enough pressure to supply public fountains, bathhouses, and homes all at once, continuously, 24 hours a day, 365 days a year. Roman aqueducts had no shut-off valve. The water never stopped flowing. The challenge was this: maintain a constant, controlled descent across dozens of miles of completely irregular terrain, with 0 electronic measuring instruments. A miscalculation and the water would stall. Or worse, gain speed and tear the entire channel apart through erosion. The instrument that made this possible was called the Chorobates, a 20-foot wooden ruler with a water channel down the center. Simple, brutal, brilliant. With it, Romans measured slopes to a precision of 0.02% across rugged terrain, under sun, rain, and wind. 7 inches of drop per mile. That was the gradient of the Pont du Gard in southern France. Picture rolling a marble on a surface with that incline. It moves, but so slowly you'd barely notice. That was exactly the ideal speed for the water. Fast enough to flow, slow enough not to destroy, to hold that millimeter-precise slope when the ground disappeared beneath their feet. When a 160-foot valley opened up in the middle of the route. They built this 160 feet tall, 3 tiers of arches, one of the most photographed structures in Europe. Individual stone blocks weighing up to 13 tons, lifted without hydraulic cranes. Just timber, rope, and a tread wheel powered by men. The logistics alone would be considered impossible by modern standards. The Anio Novus Aqueduct, one of Rome's largest, required 21 million cubic feet of material, 3 million cart trips pulled by oxen, 10,000 men working for 14 straight years. This machine was called the Polyspastos. 2 men walking inside a 13-foot wheel could lift what today requires a mid-size hydraulic crane. The total cost of Rome's aqueduct system, in today's values, would exceed $25 billion, the space program of its era. Valleys too deep to bridge with arches. Picture a valley 400 feet deep. Building an arch that tall was simply out of reach with available technology. The solution had to come from somewhere else entirely. The Roman solution was counterintuitive. Rather than going over, they went under. Water descended one side of the valley, traveled through pipes at the bottom, and climbed back up the other side. Using a principle every physics student knows today, communicating vessels. Water in a closed system always seeks the same level. Always. Here's where the villain shows up. At the base of the Bonan Valley in Lyon, the water dropped 400 feet before rising again. Think of it like pressing your thumb over a garden hose. The pressure builds. The stream turns violent. Now picture that inside a lead pipe buried at the bottom of a valley. The internal pressure reached 174 pounds per square inch, 12 times the pressure inside a fully inflated car tire. To put that in perspective, the force of the water trying to burst those pipes at the valley floor was equivalent to stacking 25 African elephants on a dining table, 25 million pounds per square foot. Romans held that fury together with nothing but lead and stone, no valves, no pressure sensors, no margin for error. The pipes were cast from thick lead, wrapped with stone clamps at regular intervals. Every joint was a critical point, a casting flaw, an air bubble in the metal, a clamp slightly off position. Any of those, and the siphon became a bomb. Water had no patience for imprecision. The man behind those calculations wasn't just a technician. He was the curator aquarum, the keeper of the waters, a high-ranking public office. He knew that if the structure failed, it wasn't his company that went under. It was him, his fortune, his reputation, his freedom. Vitruvius, the architect who codified all of this engineering, wrote it plainly. Public works with structural defects within 10 years required the engineer to rebuild them at personal expense. No insurance, no appeals, no option to dissolve the company and start over. The work was yours forever. That treatise survived 2 millennia. Vitruvius wrote 10 volumes covering everything from site selection to pressure calculations and pipelines. You can read it today. The book that Caesar's engineers used is still available. Not an interpretation, not a summary. The primary source. 2,000 years old and still relevant. If you want to understand how the greatest builders in history thought, how they solved problems we still can't replicate, the link is in the description. The 10 Books on Architecture by Vitruvius, the only engineering manual that crossed 2,000 years without losing a single idea. The system worked. For centuries, water climbed the mountain on the other side of the valley using only the energy it had gathered on the way down. Gravity against gravity, pure physics, with zero moving parts. An engineering problem solved with an elegance that still makes us uncomfortable today. Physics explained the problem. What explained the longevity? Why are these structures still standing after 2,000 years while modern bridges collapse at 50? The answer is in the material, and it's genuinely unsettling. Roman concrete isn't inert stone, it's a living material. When water seeps into microcracks, it reacts with the volcanic ash and lime and begins forming crystals inside the fracture. Those crystals grow, interlock, and fill the gap from within, as if the concrete had its own immune system. Modern concrete cracks and stays cracked. Roman concrete cracks and heals itself. The more stress it takes, the denser its internal structure becomes. It's chemistry, a chemistry that took us 2,000 years to understand, and that we still can't reproduce at industrial scale. In August 2018, the Morandi Bridge in Genoa collapsed, 51 years old. Cause of failure, corrosion of internal steel cables. At the very moment that bridge came down, the Aqueduct of Segovia was turning 2,000 years old. Still standing. Zero steel reinforcement, zero major structural intervention, just stone and chemistry. The problem with modern reinforced concrete starts on the day it's poured. CO2 in the air slowly acidifies the concrete over time. Once that acidity crosses a critical threshold, the steel's protective layer disappears. Iron turns to rust. Rust takes up more space than iron. It literally explodes the concrete from the inside out, slowly, invisibly, inevitably. Put this into financial perspective, and Roman math humiliates ours. A Roman structure cost the equivalent of $2 billion, spread over 2,000 years of service life, $1.5 million per year. A modern bridge costs $800 million, spread over 50 years, $16 million per year. The modern option looks cheaper until you run the numbers. Romans had no planned obsolescence, not because they were nobler. The law simply didn't allow it. If a structure failed within 10 years, the engineer rebuilt it at personal expense. Today, the United States carries a backlog of over $123 billion in overdue bridge repairs. Bridges quietly deteriorating. No budget, no deadline, no one accountable. 2,000 years later, it's still standing. The city around it has reinvented itself 50 times over. The empires that came after have long since turned to dust. The aqueduct remains, quiet, solid, indifferent to time, as if it's been waiting for someone to ask the right question. What the Romans had that we've lost wasn't technology, it was consequence. Their engineers knew their name was carved into the work, along with the responsibility. If it fell, they fell with it. That single detail changed everything. The choice of material, the calculations, the attention paid to what no one would ever see. We build for the next quarterly report. They built for the next millennium. The gap between those two approaches has nothing to do with technology. It's about the question asked before the first stone was ever laid. A question we somewhere along the way forgot to ask. How long does this need to last? When the answer was forever, everything changed. The materials chosen, the pressure calculations, the care given to details no one would inspect, the humility of building something larger than yourself. The next time you cross a bridge, look up at an overpass or pass under any structure designed to last 50 years. Remember this, somewhere in the south of France, a stone bridge built 2,000 years ago is still waiting for you to reach the other side. If this video changed the way you see engineering, share it with someone who needs to see it too. The link to Vitruvius is in the description. See you in the next one.